Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this big circle, and in the second question, we'll find out the area of this rectangle ABCD using two different methods. So we'll start with the first question. In the drawing, we have two circles that touch each other at this point C. In addition, we know that this is called CB, that is equal to 9 units in its length. This is called AC, that is equal to 16 units in its length. This is tangent DE, that is tangent to this small circle at point B. And also tangent DE is tangent to this big circle at this point. So when we find the point of tendency of tangent DE with this circle, this point is point M. This is point B, it is considered as an external point in relation to this big circle. So from this common external point B, we have tangent BM, that is tangent to this big circle at point M. And from the same common external point B, if we draw this straight line, it will cut the big circle at 2 points, point A and point C. In this way, if we add here, called AC. So in this drawing, you can implement rule 10. According to rule 10, if from this common point P, you will draw tangent PT to this circle, tangent PT is tangent to this circle at point T, and from the same common point P, you will draw this straight line. The straight line cuts the circle at 2 points, A and B. In this way, created here called AB. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. You can definitely implement rule 10 in our drawing. Why? Because in our drawing, from this common point B, we have tangent BM, that is tangent to this circle at point, to this big circle at point M. And from the same common point B, we have also, if we draw this straight line, it will cut the circle at 2 points A and C. This way, created here, called AC. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true, that BM squared equals to BC times BA. Again, BM squared equals to BC times BA. So I write it down. BM squared equals to BC times BA. Repeat again, if we focus on the common point B, according to rule 10, the following equation is true, that BM squared equals to BC times BA. BM is the missing tangent, so we leave it as it is. So BM squared equals to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So total, according to rule 10, we found out that BM square equals to 9 times 25. Here, we take a root out of this equation, and we get that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So the length of tangent BM is 15 units. So tangent BM equals to 15 units in its length. In the next step, we will do a construction. That is to say, from this point C, we will draw a common tangent that belongs to both circles. And we will define the touching point of the common tangent with tangent DE. This point is point N. So actually, tangent NC is a common tangent that belongs to both circles. Tangent NC is tangent to this small circle at point C, and tangent NC, the common tangent NC, is also tangent to this big circle at the same point C. Therefore, tangent NC is a common tangent that belongs to both circles. In the next step, we will focus on this common external point N. From this common external point N, we have two tangents to this small circle, tangent NB and tangent NC. So here we can implement rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, we have a circle, and this is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can implement rule 2 in our drawing. Well, because in our drawing, from this common external point N, we have two tangents to this small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. So in the next step, I will copy triangle CNB in a new page, and we will analyze this triangle CNB. So actually, this is triangle CNB that I copied from the original drawing. This triangle CNB, side CN equals to side NB according to rule 2. And we have the rule that states that in front of equal sides in the triangle there are equal angles. Repeat again, in front of equal sides in the triangle there are equal angles. So in front of this side CN, we have this angle that is actually angle CBN, and in front of this side NB, we have this angle that is actually angle NCB. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes, according to the rule that I mentioned. So if the size of this angle NCB is alpha, then the size of this angle CBN must be also equal to alpha, because they must be equal to each other according to the rule that I mentioned. So in total, we found out that angle NCB equals to alpha and angle NBC also equals to alpha. So actually, this is angle NCB that is equal to alpha, and this is angle CBN that is also equal to alpha. In the next step, we'll join point C and M together by a straight line. And we'll continue to focus on the common external point N. From the common external point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. So in the next step, I'll copy triangle C and M in a new page, and we will analyze this triangle C and M. So actually, this is triangle C and M that I call it from the original drawing. In this triangle C and M, side CN equals to side NM according to rule 2. And according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles, we get that in front of this side CN, we have this angle, this is angle CMN. In front of this side NM, we have this angle, that is angle NCM. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, according to the rule that I mentioned. So in total, we found out that angle NCM equals to beta and angle CMN also equals to beta. This is angle NCM that is equal to beta, and angle CMN also equals to beta. In the next step, I'll copy the big triangle CMB in a new page, and we'll analyze this big triangle, triangle CMB. The big angle MCB equals to alpha plus beta. So actually, this is the big triangle CMB that I copied from the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in this triangle CMB must be equal to 180 degrees. So which angles we have in triangle CMB? We have this angle that is alpha, plus this angle that is beta, plus the big angle that is alpha plus beta or beta plus alpha. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation, we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta, so in total we should find out that 2 alpha plus 2 beta equals to 180 degrees. Here we divide this equation by 2, and finally we get that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So the big angle alpha plus beta is a right angle. So actually the big angle is angle MCB, and angle MCB is a right angle. This is the big angle MCB, and it is a right angle. It is equal to 90 degrees in size. It is given us the question that AB is a straight line. Again, AB is a straight line according to what is given us the question. So if we focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll join points A and M together by a straight line. By joining points A and M, we can do chord AM. chord AM is a chord in this big circle. Again, chord AM is a chord in this big circle. And we have also here peripheral angle ACM. This is peripheral angle ACM, and the size of peripheral angle ACM is 90 degrees according to rule 3. So this is a right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So I'll put quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. Here in the drawing we have a circle. This is peripheral angle MAN. And because of the fact that peripheral angle MAN is a right angle, that is to say it is equal to 90 degrees in its size, this peripheral angle MAN must subtend on the diameter of the circle. And because of the fact that peripheral angle MAN subtends on MN must be the diameter of this circle according to this rule, rule 5. So any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So we can definitely implement rule 5 in our drawing. Why? Because in our drawing we have inside this big circle we have peripheral angle ACM that is equal to 90 degrees in its size. And therefore, according to rule 5, peripheral angle ACM must subtend on the diameter of this circle. And because of the fact that peripheral angle ACM, that is a right angle, subtend on AM must be the diameter of this big circle. So we can find out that AM is the diameter, chord AM is the diameter of this big circle. So I'll write it down. According to rule 5, we actually found out that chord AM is the diameter of the big circle. And again, this is called AM, that is the diameter of this big circle according to rule 5. And we also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. AM is the diameter of this big circle, and therefore the center of this big circle must be located on AM. So here, this is the center of this big circle. We define the center of this big circle as O. Point O is definitely located on AM, that is the diameter of this big circle. So point O is the center of this circle. Point O is the center of this big circle. Point M is the point on the big circle itself. Therefore, OM is the radius of this big circle. We define the radius of this big circle OM as R. And because of the fact that the radius OM of this big circle, the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So, in the next step, I'll copy the right big triangle A and B in a new page, and we will implement the Pythagoras theorem on this right big triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AB, and the length of side AB is 16 plus 9, that is 25. Side AM is the missing side, and side MB equals to 15 units in itself according to rule 10. So here by PT is the version for Pythagoras theorem. So actually, this is the right big triangle A and B that I copied from the original drawing. This right triangle A and B according to the Pythagoras theorem, AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. Again, AB squared equals to AM squared plus MB squared. So I'll write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. The hypotenuse AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we leave it as it is, so it is AM squared plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total we found out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 times 225 is 400, so 400 equals to AM squared. Here we take a root out of this equation, and finally get that AM, the missing side, AM equals to the square root of 400, this is 20. Again, the square root of 400 is 20. So the missing side AM equals to 20 units in its length. But we have already found out that chord AM is the diameter of the big circle. Again, the missing side is also chord AM, and chord AM is the diameter of this big circle. And because of the fact the diameter of this big circle equals to 20 units in its length, the radius R must be equal to half of it. So the radius R of the big circle must be equal to the diameter AM over 2. The diameter AM is 20, and 20 over 2 is 10. So in total we found out that the radius R of the big circle is equal to 10 units. Repeat again, the radius R of this big circle equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. So in total we found out that the area of this big circle is equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. So we found out that the area of this big circle, that is the area that we are looking for in this question, it is equal to either 100 pi square units, or in terms of numbers, it is equal to 314.159 square units. And that's it, that's up to the question. Repeat again, we found out actually that the area of this circle, the area of this big circle, it is equal to either 100 pi square units, so in terms of numbers, it is equal to 314.159 square units. So we finish with the first question. In the next step, I will present you the second question, and we solve the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So, in the drawing we have rectangle ABCD, and we have also this semicircle. We know that side AM equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So, I'll start with the first method. First of all, because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle ABCD must be equal to 90 degrees in their sizes. So this angle equals to 90 degrees. this angle also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle also equals to 90 degrees. We define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. So point O is the center of this semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to x units in its length according to our definition. We define the point of tendency of tangent DC with this semicircle. This point is point E. And we join points O and D together by a straight line. So what is the definition of line segment OE? Line segment OE starts from point O, that is the center of this semicircle, and ends at point E, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this semicircle, that is equal to x units in its length, according to our definition. And because of the fact that the radius OE that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to rule 1. So by doing this construction, you can deduce the small quadrilateral DEOA. Inside this small quadrilateral DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth angle must be equal to 90 degrees in its size. So inside quadrilateral DEOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral DEOA as a rectangle because it has 4 right angles. Quadrilateral DEOA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA, but EO is x, therefore DA must be also equal to x units in its length. In the next step, we define this line segment OB as A. We define this line segment MB as B. And we join points O and M together by a straight line. What is the definition of line segment OM? Line segment OM starts from point O, that is the center of the semicircle, and then at point M, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle that is equal to x units in its length. In the next step, I'll copy the right triangle OMB in a new page, and we'll implement the Pythagoras theorem on this right small triangle OMB. Here by PT is the preparation for Pythagoras theorem. So actually, this is the right small triangle OMB that I comment from the original drawing. According to the Pythagoras theorem, in this right triangle OMB, MO squared, that is the square of the hypotenuse, equals to MB squared plus BO squared. Again, MO squared equals to MB squared plus BO squared. So I write it down. This will be equation 1. So MO squared, that is the square of the hypotenuse, is equal to MB squared plus BO squared. MO is x, therefore MO squared is x squared. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus BO squared. BO is A, therefore BO squared is A squared. So in total, according to equation 1, we actually found out that x squared equals to B squared plus A squared. In the next step, I'll copy the right big triangle, triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right big triangle, triangle A and B. The hypotenuse AM of this right triangle A and B is equal to 5 units in its length, according to what is given as the question. Side AB equals to B units according to our definition, and side AB in total equals to x plus A. So actually, this is the right big triangle A and B that I covered from the original drawing. This right triangle A and B, according to the Pythagoras theorem, MA squared equals to MB squared plus BA squared. Again, MA squared equals to MB squared plus BA squared. So I'll write it down. This will be equation 2. MA squared, that is the square of the hypotenuse, equals to MB squared plus AB squared. The hypotenuse MA is 5, therefore MA squared is 5 squared, that is 25. And it is equal to MB squared. MB is B, therefore MB squared is B squared plus AB squared. AB is x plus A, therefore AB squared is x plus A squared. So in total, according to equation 2, we should find out that 25 equals to B squared plus x plus A squared. So 25 equals to B squared plus x plus A squared. X plus A squared equals to x squared plus A squared plus 2 times x times A. On the right side of this equation 2, we have the expression B squared plus A squared. But according to equation 1, we have only found out that B squared plus A squared equals to x squared. Therefore, we substitute B squared plus A squared in this equation 2, by x squared from this equation 1. We do it now, we get that according to equation 2. $25 equals to B squared plus A squared is x squared. According to equation 1, we have x squared again plus 2xa. So in total, according to equation 2, we actually found out that $25 equals to x squared plus 2xa. So 25 equals to x squared plus x squared is 2xa, 2x squared plus x squared is 2x squared plus 2xa. So total according to equation 2, we shall find out that 25 equals to 2x squared plus 2xa. Here we divide this equation 2 by 2. And we get that according to this equation 2, 25 over 2 is 12.5. And it is equal to 2x squared over 2 is x squared plus 2xa over 2 is xa. So total according to equation 2, I shall find out that 12.5 equals to x squared plus xa. So 12.5 equals to x squared plus xa. Here we take out x as a common factor from those two expressions. So x was taken out as a common factor. What is left from x? Well, after we took from it x as a common factor, what is left is actually x. And what is left from xa after we took x from it as a common factor, what is left is actually a. So in total, according to equation 2, we shall find out that 12.5 equals to x times x plus a. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So in total, we found out that the area of rectangle ABCD equals to AB times DA. AB is x plus a, and dA is x. So in total, we found out that the area of rectangle ABCD equals to x plus a times x. Again, the area of this rectangle ABCD equals to x plus a times x. But because of the fact that x plus a times x is 12.5, we substitute x plus a times x here by 12.5. So in total, we found out that the area of rectangle ABCD equals to 12.5 square units. That is the answer to the question. Repeat again. We actually found out that the area of this rectangle ABCD equals to 12.5 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is rectangle, all those four angles inside rectangle ABCD are right angles. So this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. We define the center of this semicircle. This point is point O, and we define the radius of this semicircle as x, exactly as we did in the first method. So point O is the center of the semicircle, point A is the point of the semicircle itself, so for OA is the radius of this semicircle, that is equal to x. We have already found out in the first method that dA equals to x. So I will not repeat on the same explanation. dA equals to x according to the first method. In the next step, we define this line segment OB as A. And we define this point as point N. And we'll join points M and then together by a straight line. By joining points M and N, we get the depth, peripheral angle MN, peripheral angle AMN. This is peripheral angle AMN. And because of the fact that peripheral angle AMN subtend on AN, that is the diameter of this semicircle, peripheral angle AMN must be equal to 90 degrees in its size, according to rule 7. So repeat quickly on rule 7. According to rule 7, if the peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. Inside this circle we have chord AB. Chord AB is the diameter of this circle, and because of the fact that peripheral angle ACB subtend on AB, that is the diameter of this circle, peripheral angle ACB must be equal to 90 degrees in its size. But again, because of the fact that peripheral angle ACB subtend on AB, that is the diameter of this circle, peripheral angle ACB must be equal to 90 degrees in its size according to this whole rule 7. So somebody mentioned we can implement rule 7 in our drawing because of why? Because of the fact that peripheral angle AMN subtend on AN, that is the diameter of this semicircle, therefore peripheral angle AMN must be equal to 90 degrees in its size according to rule 7. Okay. In the next step, we define this angle as angle alpha, and we focus on this right triangle, triangle AMN. In the right triangle AMN, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, we focus on this right triangle, triangle A and B. In this right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the same rule that states that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to triangle A and B, and angle A also belongs to the right triangle, triangle AMN. So angle A is a common angle that belongs to both triangles. So in the next step, I'll copy the right triangle A and B and the right triangle AMN in the equation. We prove that those two right triangles are similar to each other according to angle similarity rule. side AM equals to 5 units in its length, according to what is given as the question. Side AB in total equals to x plus a. Line segment AN is the diameter of the semicircle. Repeat again. Line segment AN is the diameter of the semicircle, and because of the fact that the radius of this semicircle equals to x, the diameter must be equal to 2x. So AN equals to 2x. Since the diameter of the semicircle is equal to 2x. Repeat again that angle A is a common angle that belongs to both triangles. It belongs to the right triangle AMB, and it also belongs to the right triangle AMN. So actually, those are the two right triangles that are coming to the original drawing. This is triangle AMB, this is triangle AMN. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually, this is angle ABM. In the right triangle AMB, and it is equal to this angle, that is actually angle AMN. In the right triangle AMN, they are both equal to 90 degrees, and therefore they are equal to each other. This is angle A, that is a common angle that belongs to both triangles. Here, angle A. Because this is also put in this triangle, triangle AMB. So angle A is a common angle that belongs to both triangles. So if we relate to angle A as it belongs to the right triangle AMB, it will be defined as angle MAB. And angle A equals to itself. So if we relate to angle A as it belongs to this triangle, triangle AMN, it will be defined as angle MAN. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle AMB. In the right triangle AMB, and it is equal to this angle, that is actually angle ANM. In the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles of this right triangle AMB are correspondingly equal to all the triangles of this right triangle AMN, and therefore those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. So triangle A and B, this triangle A and B is similar. This is the sign of similar to this triangle AMN. According to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of this right triangle AMB over side AM of this right triangle AMN. Repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AM of the right triangle AMB over side AN of the right triangle AMN equals to side AB of the right triangle AMB over side AM of the right triangle AMN. AM is 5. According to what is given as the question, over AN. AN is the diameter of the semicircle, that is 2x, over AB. AB is x plus A, over AM, that is 5. So in total, according to equation 1, we shall find out that 5 over 2x equals 2x plus A over 5. Here we'll cross multiply this equation 1, and finally get that 5 times 5 is 25, so 25 equals to 2x times x plus A. Here we divide this equation 1 by 2, and finally get that according to this equation 1, 25 over 2 is 12.5, so 12.5 equals to 2x over 2 is x, so in total this expression equals to x times x plus A. So according to equation 1, we have found out that 12.5 equals to x times x plus A. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Repeat again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So in total, we actually found out that the area of rectangle ABCD equals to AB times DA. AB is x plus A, and DA is x. So in total, the area of rectangle ABCD equals to x plus A times x. But x plus 8 times x is 12.5 according to equation 1. So we'll substitute x plus 8 times x here by 12.5. So in total we shall find out that the area of rectangle ABCD equals to 12.5 square units. So in both methods we found out the area of this rectangle ABCD equals to 12.5 square units. So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this big circle. So in the drawing we have two circles that touch each other at this point C. In addition, we know that this is called CB, that is equal to 9 units in its length. This is called AC, that is equal to 16 units in its length. This is tangent DE, that is tangent to this small circle at this point B, and tangent DE is also tangent to this big circle at this point M. Point B is considered as an external point in relation to this big circle. So from this common external point B, we have tangent VM that is tangent to this big circle at point M. In addition, from the same common external point B, if we draw this straight line, it will cut the big circle at 2 points, point C and point A. In this area, called AC. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. But again, if we focus on the common start point B, then according to rule 10, the following equation is true: that BM square equals to BC times BA. BM is the missing tangent, so we leave it as it is. So BM square equals to BC. BC is 9 times BA. BA in total is 9 plus 16, that is 25. So in total, BM square equals to BC, that is 9 times BA, that is 25. So BM square equals to 9 times 25. Here we took out of this equation, and finally found out that BM equals to the square root of 9, that is 3, times square root of 25, that is 5. So in total, BM equals to 3 times 5, that is 15. So the length of this tangent BM is 15 units, according to rule 10. In the next step, we did the construction. That is to say, from this point C, we drew a common tangent that belongs to both circles. And we defined the point of the touching point of the common tangent and tangent DE. This point is point N. So actually, the common tangent CN is tangent to both circles. The common tangent CN is tangent to this small circle at point C, and the common tangent CN is also tangent to this big circle at the same point C. So CN is defined as a common tangent that belongs to both circles. In the next step, we focus on this common external point N. From this common external point N, we have two tangents to the small circle, tangent NB and tangent NC. And according to rule 2, they are equal to each other. That is to say, NB equals to NC. In the next step, I copy triangle CNB in an equation, and we analyze this triangle CNB. So actually, this is triangle CNB, that according to the original drawing, according to rule 2, side CN equals to side NB. And we have the rule that says that in front of equal sides in the triangle, there are equal angles. So in front of this side CN, we have this angle, that is angle CBN, and in front of this side NB, we have this angle, that is angle NCB. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, according to the rule that I mentioned. So in total, we should find out that angle NCB equals to alpha and angle CBN also equals to alpha. In the next step, we join point C and M together by a straight line. And we continue to focus on this common start point N. From this common start point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to rule 2, they are equal to each other. That is to say, NC equals to NM. In the next step, I copied triangle CMN in a new page and we analyze this triangle CMN. So okay, this is triangle CMN that I copied from the original drawing. According to rule 2, side CN equals to side MN. And according to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle CMN, and in front of this side MN we have this angle that is angle MCN. And because of the fact that those two angles are located in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta according to the rule that I mentioned. So in total, if we found out this angle MCN equals to beta, and this angle CMN also equals to beta. In the next step, I copied the big triangle MCB and we analyze this big triangle MCB. So actually, this is the right triangle MCB that I copied from the original drawing. According to the rule that said that the sum of the angles in any triangle is equal to 180 degrees, we get that the sum of the angles in this triangle MCB must be equal to 180 degrees. So which angles we have in this triangle MCB? We have this angle that is beta plus this angle that is alpha plus this big angle that is alpha plus beta. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So in this side of the equation we have alpha plus alpha, that is 2 alpha, beta plus beta is 2 beta, so 2 alpha plus 2 beta equals to 180 degrees. Here we divided the equation by 2 and finally found out that alpha plus beta equals to 180 degrees over 2 is 90 degrees. So the big angle alpha plus beta is a right angle, or angle MCB is a right angle. So actually, this is the big angle MCB that is a right angle. It is given as a equation that AB is a straight line. Okay, AB is a straight line according to what is given as the equation. So if you focus on the left side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the left side of AB at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size, according to rule 3. So, in the next step, we join points A and M together by straight line. In this way, we created chord AM. Chord AM is a chord in this big circle. And in the drawing, we have here peripheral angle ACM, that is a right angle according to rule 3. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. Because of the fact that peripheral angle ACM, that is a right angle, subtend on chord AM must be the diameter of this big circle according to rule 5. Again, chord AM must be the diameter of this big circle according to rule 5. Okay, again, according to rule 5, chord AM is the diameter of the big circle. And we also know that the center of any circle must be located on the diameter of the circle. Again, the center of any circle must be located on the diameter of the circle. And because of the fact that AM is the diameter of this big circle, the center of this circle must be located on chord AM. So here, this is the center of this big circle. We define the center of this big circle as so. Point O is definitely located on AM, that is the diameter of this big circle. So point O is the diameter of this big circle, point M is the point on the big circle itself, therefore OM is the radius of this big circle. We define the radius of this big circle as R, so OM equals to R, it is the radius of this big circle. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I copied the right big triangle A and B in a new page, and we implemented the Pythagoras theorem in this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. the ref of the hypotenuse AB is 16 plus 9, that is 25. AM is the missing side, and MB equals to 15 units in itself, according to rule 10. So okay, this is the right triangle A and B that are coming from the original domain. In this right triangle A and B, AB squared, that is the square of the hypotenuse, must be equal to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so as it is, plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, according to the Pythagoras theorem, we found out that 625 equals to AM squared plus 225. Here we subtract 225 from this equation, and finally found out that 625 minus 225 is 400, so 400 equals to AM squared. Here we took out of this equation, and finally found out that the missing side AM equals to the square root of 400, that is 20. AM equals to 20 units instead. But we only found out that chord AM is the diameter of the big circle. This is chord AM, that is the diameter of the big circle, and because of the fact that the diameter of this big circle is equal to 20 units in itself, the radius must be equal to half of it. This is to say, the radius R must be equal to the diameter AM over 2. AM is 20, therefore the radius R must be equal to 20 over 2, that is 10. So in total we should find out that the radius of this big circle R equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of the big circle must be equal to pi times the radius of the big circle squared. The radius of the big circle is 10, therefore the radius squared is 10 squared. So in total, the area of the big circle must be equal to pi times 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. So in total, we should find out the area of this big circle equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. So we finish with the first question. In the next step, I presented you the second question, and we solved the second question in two different methods. Our mission in this second question is to find out the area of this rectangle ABCD. So, in the domain we have rectangle ABCD, and we have this semicircle. Line segment AM equals to 5 units in itself. Again, our mission is to find out the area of this rectangle ABCD. So we started with the first method. First of all, because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. We define the center of this semicircle. This point is point O, and we find the radius of this semicircle is x. Point O is the center of the semicircle, point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle, that is equal to x units in itself, according to our definition. In the next step, we define the point of tendency of tangent DC with this semicircle. This point is point E, and we join points O and D together by straight line. Point O is the center of the semicircle, point E is the point on the semicircle itself, therefore OE is the radius of the semicircle, that is equal to x units in itself. And because of the fact that the radius OE, that is equal to x, the radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle, and whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If this is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in total, inside the big quadrangle, inside the small quadrangle DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus, actually inside this quadrangle DEOA we have 1, 2, 3 right angles. So the sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees. That is the sum of the angles in any quadrangle. Therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrangle DEOA we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be a rectangle if not a square. So we relate to this small quadrangle DEOA as a rectangle because it has 4 right angles. But we also know the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But EO is x, therefore the opposite side DA must be also equal to x units in its length. In the next step, we define this line segment OB as A, and we define this line segment MB as B. We join points O and M together by side line. OM is the radius of this semicircle, is equal to x. In the next step, I copy the right triangle O and B in a new page, and we implemented the Pythagoras theorem on this right triangle O and B. Okay, this is the right triangle O and B that I copied from the original drawing according to the Pythagoras theorem. In this right triangle O and B, MO square equals to MB square plus BO square. MO is x, therefore MO square is x square, and it is equal to MB square. MB is B, therefore MB square is B square plus BO square. BO is A, therefore BO square is A square. So in total, according to equation 1, we found out that x square equals to B square plus A square. In the next step, I copied this right big triangle A and B in a new page, and we implemented the Pythagoras theorem on this right big triangle A and B. The hypotenuse AM is 5 according to what is given as the question, MB is B according to our definition, and AB in total equals to x plus A. So according to the Pythagoras theorem in this right triangle A and B, MA square, that is the square of the hypotenuse, equals to MB square plus BA square. MA is 5, therefore MA square is 5 squared, that is 25, and it is equal to MB square. MB is B, therefore MB square is B square plus BA square. BA is x plus A, therefore BA square is x plus A square. So in total, 25 equals to B square plus x plus A square. X plus A square is x square plus A square plus 2xa. In the right side of equation 2, we have the expression B square plus A square, but according to equation 1, B square plus A square equals to x square. So we can substitute B square plus A square by x square. We did it, and we found out that in total 25 equals to B square plus A square is x square according to equation 1. We have x square again plus 2xa. So in total, according to equation 2, we actually found out that 25 equals to x square plus 2xa. So 25 equals to x square plus x square is 2x square plus 2xa. Here we divided this equation 2 by 2, and finally found out that 25 over 2 is 12.5, 2x square over 2 is x square, and 2xa over 2 is xa. So in total, we actually found out that according to equation 2, 12.5 equals to x square plus xa. So 12.5 equals to x square plus xa. So we took out x as a common factor from those two expressions. So x was taken out as a common factor. What is left from x square after we took from it x as a common factor? What is left is actually x. And what is left from xa after we took from it x as a common factor? What is left is x. What is left is A. Okay, so in total, according to equation 2, we actually found out that 12.5 equals to x times x plus A. According to equation 2, 12.5 equals to x times x plus A. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? What is the area of rectangle ABCD? Actually, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So total, the area of rectangle ABCD must be equal to AB times DA. AB in total is x plus A, and BA is x. And again, AB is x plus A, and DA is x. So in total, the area of rectangle ABCD equals to x plus A times x. But according to this equation 2, x plus A times x is 12.5. So we substitute x plus A times x by 12.5, and actually found out in total the area of rectangle ABCD equals to 12.5 square units. Okay, so we finish with the first method. Again, the area of this rectangle ABCD according to the first method is equal to 12.5 square units. So we finish with the first method. In the next step, I presented to you how to find out the area of this rectangle ABCD according to the second method. So first of all, because of the fact that ABCD is a rectangle, all those four angles inside rectangle ABCD are right angles. We define the center of this semicircle, this point is point O, and we define the radius of this semicircle as x. So OA is the radius of the semicircle, is equal to x according to our definition. According to the first method, we have already found out that dA equals to x, so I'll not repeat to the same explanation. dA equals to x, units in its length according to the first method. In the next step, we define this line's length OB as A. In addition, we define this point as M, and we join points M and N together by a straight line. By joining points M and N, we can actually create here peripheral angle AMN. This is peripheral angle AMN that's obtained on AN, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that's obtained on the diameter of the semicircle or circle must be equal to 90 degrees in its side. Again, according to rule 7, any peripheral angle that's obtained on the diameter of a circle or semicircle must be equal to 90 degrees in its sides. And because of the fact that peripheral angle AMN subtend on AN, that is the diameter of this semicircle, it is equal to 90 degrees in its side according to rule 7. In the next step, we define this angle as alpha and focus on the right triangle AMN. On the right triangle AMN, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on this right triangle A and B. In this right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to this right triangle A and B, and angle A also belongs to this right triangle AMN. So angle A is a common angle that belongs to both triangles. In the next step, I copy the right triangle A and B, and this right triangle AMN in the new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So, side AN is the diameter of the semicircle. The radius of the semicircle is x, therefore the diameter must be equal to 2x. So AN equals to 2x, AB equals to x plus A, AM equals to 5 units in itself, according to what is given as the question. So those are the two right triangles. This is triangle A and B. This is right triangle AMN that according to the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle A, that is a common angle that belongs to both triangles. You can see that angle A also belongs to this triangle, triangle AMN. So angle A is a common angle that belongs to both triangles. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the three angles on this right triangle A and B are corresponding equal to all the three angles of this right triangle AMN, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM of this right triangle A and B over side AN of this right triangle AMN equals to side AB of this right triangle A and B over side AM of this right triangle AMN. Repeat again. We will derive that side AM of the right triangle A and B over side AN of the right triangle AMN equals to side AB of the right triangle A and B over side AM of the right triangle AMN. AM is 5, AN is 2x, AB is x plus A, and AM is 5. So in total, according to equation 1, we shall find out that 5 over 2x equals to x plus A over 5. Here, of course, multiply this equation, equation 1, and finally found out that according to this equation, equation 1, 5 times 5 is 25. So 25 equals to 2x times x plus A. Here we divided this equation, equation 1 by 2, and finally found out that 25 over 2 is 12.5, 2x over 2 is x, so in total this expression equals to x plus x times x plus A. So in total, according to equation 1, we have found out that 12.5 equals to x times x plus A. Our mission is to find out the area of this rectangle, rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of the rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is DA. So in total, the area of rectangle ABCD must be equal to AB times DA. AB in total is x plus A, and DA is x. Again, AB is x plus A, and DA is x. So in total, the area of rectangle ABCD must be equal to x plus A times x. But according to equation 1, x plus A times x is 12.5. Therefore, we substitute x plus A times x by 12.5. So in total, we shall find out that the area of rectangle ABCD equals to 12.5 square meters. So in both methods, we found out the area of this rectangle ABCD is equal to 12.5 square meters. Okay, thank you very much.